Okay, so we have another one of these questions. Draw and name the product when a vast excess of HBr, if you can make that out there, another hydrogen halide, hydrogen bromide, is reacted with the following alkyne. Kyne meaning that you have a triple bond. Okay, so we have a triple bond between, we have the longest chain of 3 carbons, and the triple bond is from the first carbon to the second. So this is going to be an alkyne with a 1 in there. Prop-1-ine, I think is what it would be. Okay, so in any case, we have a vast quantity of HBr, which means there's going to be plenty of ions, I guess, and from that then we are going to look at the mechanism and then how we end up with this product. Alright, so then there's a whole lot of things going on with this hydrogen bromide and this electron rich area that we have in the alkyne. Okay, and what I've done is I've just color coded the electrons so that it's clear then where electrons get transferred to and from. Okay, so yeah, we do indeed have an electron rich area, plenty of negative charge. Okay, so if we have a HBr molecule that jumps into this Goliath's den, if you like, right here, what's going to happen is that the electron, okay, so there's a covalent bond between the HBr. You've got, what have you got? You've got 2 electrons in a bond pair. Okay, if you can imagine that. Let me color code them in actually. Alright, so there's our bond pair of electrons between the H and the Br, the covalent bonding pair of electrons, one from the hydrogen and one from the bromine involved in the bond. Well, in the presence of this negative Goliath's den area right here, it's all very negative altogether, what's going to happen is that this much more electronegative bromine is going to have the electron, if you like, well, it's going to be repelled from the hydrogen, and its tendency will go to the more electronegative bromine. So this negative area here with this negative charge will cause the electron on the hydrogen to be repelled onto the bromine, and the bromine, being more electronegative, is quite happy to do that. Okay, so then when you have a bromine negative, we have one more extra electron in there than we should have, so this goes negative. We have one less electron on the hydrogen, this goes positive, and then we have a whole setup then where we have to go looking at bond breaking, and when the bonds do break, who delivers on the feast, who takes electrons and who delivers it on electrons. So let's go look at that. Okay, so in the presence now of, well, we have these 2 agents here. We have an electrophilic and a nucleophilic substance right here. Okay, so the electrophilic needs electrons. The bromine here, with its excess of electrons, now it has 1 extra electron, given that in the bond pair now it's taken the electron off the hydrogen, so it has these 2 electrons for itself now. This is going to be nucleophilic, and it's got plenty of electron to give. Okay, so then, okay, we have a little bit of Markovnikov's rule going on here then, in terms of, well, look at when the bonds do break, which one is going to lose the electron. Okay, so we're talking about our triple bond here now. We're saying, well, okay, bonds are going to break, but then where are the electrons going to be lost from? Will this electron be lost off this carbon, or will this electron be lost off this carbon? And by Markovnikov's experimental work, it's found that the carbon that forms the center of the bond, okay, so if we have a secondary carbon, this would be a primary carbon. It's only bonded to 1 carbon on its left, whereas this carbon here is bonded to 2 carbons, so it's a secondary carbon. And what we find is that this is the one that is more adept at losing its electron, because it's in a region where it's got its carbon friends either side, bromide, and they may well help to share out some of their electrons in their electron cloud. Okay, so this is the carbon that is going to lose its electron. It's a secondary carbon bonded to a carbon here and a carbon here. So we're going to get a swing, if you like. This one is going to swing up the way. It's going to swing anti-clockwise, actually through 180 degrees, because you can see I've color coded it here. This red electron that was here is now over here, so it's rotated by 180 degrees clockwise. And which other one? The green one, it's done a 90-degree anti-clockwise, so this electron here is now down here. Okay, so these have electrons then, well, we have lone pairs of electrons is what we have, which means that one of the electrons is not bonded to anything. We have a electrophilic agent here which needs electrons, so therefore the H plus is going to go straight there for that electron. And given that we have much quantities of H plus Br, these radicals, we're also going to have another H. It's not difficult to imagine that another H is also going to bond over here, and that will take care of the electrophilic part of it, these needed electrons, and they do have them. But then we have lost electrons here. We've lost the red one that was here. This red one is gone now from that central carbon, and the green electron is also gone from that carbon as well. So therefore we have a deficit. We have a carbocation, if you like, with a double positive. Okay, so this carbon here needs 2 electrons. It has lost 2 electrons, so therefore it needs 2 electrons. Well, the agent who has plenty of electrons is the bromine, and there it is right there. It has an extra electron which it can donate for a bond pair, and this is exactly what happens, and you end up getting the purple and the purple electron here forming a bond pair. So basically this lone pair becomes a bond pair when it bonds with the carbon. Let me just go color code that again. Alright, so there you see it then. We see the bromine has donated its lone pair to forming a bond pair with the carbon that had a deficit of electrons. It needed electrons, and so therefore we have that. And again, by definition, do we have 4 bonds around the carbon? Yes, indeed we do. 1, 2, 3, 4. So it has a full octet, 8 electrons on the outer shell. And similarly here again too, we have 4 bonds. So therefore we have 8 electrons. We have a complete octet there as well. Alright, so then we're looking at the reduction of an alkyne to an alkene. Okay, so reduction is the idea that you gain electrons, okay, but there is another definition where it says that hydrogen is bonded. Okay, something is reduced if hydrogen has been added to it. Okay, so therefore we're talking about actually both in this case. Okay, the two are interchangeable. Addition of hydrogen and gain in electrons, which is what reduction is, actually happens. Okay, so first of all let's look at the hydrogen and the way it's bonding covalently. It has sharing its single electron, covalent bond, but in the presence of the catalyst, the hydrogen is in a position then to break its bonds, and so therefore you end up with 2 hydrogen radicals, if you like. So we have the green electron going back and it becoming a H negative, and we also have a H negative here, the orange colored one. Okay, so if we then look at our alkyne with its triple bond, we're also talking about the fact that it changes to an alkene, and an alkene has a double bond, which means that one of the bond pairs has broken. Okay, so that means that we have an electron here, and we have an electron over here as well. Okay, so we have the purple electrons unbonded, if you like, unpaired as well. Unpaired electrons is neither a lone pair nor a bond pair. So we just have an electron there, and it needs to gain an electron to become a bond pair. okay, or a lone pair, but in this case it's going to be a bond pair that we're having. And how is this occurring? Well, we have hydrogen in the mix here, and the hydrogen has an extra electron. We have an electron that is neither a bond pair nor a lone pair, it's unpaired, and so therefore it's quite happy then to accept an electron from the hydrogen and form a bond pair. And we have the green electron from here forming this bond pair, and we have the orange electron from the other hydrogen forming the other bond pair. And this is the addition of hydrogen, but it is also the gain of electrons as well. Okay, the net result of this is that we have had a gain of 2 electrons. We only had the 2 purple, if you remember, from over here, as well as all the others, but now we also have a green and an orange. So we've added hydrogen, which is called reduction, but we've also added electrons, which is also reduction by both definitions.